A block of mass 4.8 kilograms is placed on the edge of a rough surface of height 0.5, h equals 0.52 meters. Okay? So it looks like it's 0.52 meters. Okay? As shown above. The block is released and moves until it stops momentarily after compressing a horizontal spring with a spring constant of, looks like 2 newtons per meter by a compression distance of 12.1 centimeters or 0.121 meters. Find the work done by friction. Okay. So for this, we're going to use the idea of conservation of energy. So I'm going to say energy initial equals energy final. And this is true for conservation of energy, which it's not going to be true here. That's supposed to be conservation. I know, my handwriting is tragic. It's not going to be true here because there's friction. So energy initial is going to be bigger than energy final, because we're going to lose some energy. It's not conservative because we're going to lose some energy due to friction. So what I'm going to do is I'm going to say that the energy lost due to friction, there we go, is going to be energy initial minus energy final. And that should give us some sort of positive number of it, and that'll represent the energy lost. So what we want to do then is we want to look at what energy initial is and energy final. So coming up here, I'm going to say that energy initial is going to be energy potential plus energy kinetic. I'm going to break up energy potential into energy potential gravitational plus energy potential spring, and then energy kinetic, I'm just going to leave as energy kinetic. So when it's at the top of the hill, there's no spring involved. It's just at the top of the hill. So that's going to be 0. And energy gravitational, that's just going to be mass times gravity times height. And then its speed is 0. So since energy kinetic is 1/2 mv squared, v is 0, so that's 0. So this is going to be its initial energy that it has. Energy final, same idea, energy potential gravitational plus energy potential spring plus energy kinetic. Now, you might be like, well, how many different types of potential energy are there? How many different types of kinetic energy there are? Or at least formulas for such? And the answer is many. So energy potential is just energy that's due to position. Energy kinetic is energy that's due to motion. So in case of a spring, energy potential spring is due to how compressed the spring is. Energy potential gravity is how far apart two masses are. So we're going to call this 0, height. So energy potential due to gravity is going to be 0. It's going to momentarily come to a stop because it says momentarily comes to a stop. And energy potential spring is going to be 1/2 k delta x squared, where delta x is how compressed the spring is. All right. So now we're going to come down to an idea here where we have non-conservative force. Therefore, we have energy lost. So conservation of energy does not apply. But specifically, since we have only one loss of energy here, and that's due to friction, we can say that, all right, the energy we lost is going to be the difference of our initial energy minus our final energy. And so I'm going to say energy initial is mgh, like we talked about up here, minus 1/2 k delta x squared. Putting some numbers into that, we have 4.8. I'm going to call gravity 10. Nah, I'm going to call it 9.8. I'm not going to try to do this in my head. I am smarter than that. So h minus 1/2 times 2, I think that's a period, so it's going to call that 2 newtons per meter, times 0.121 meters, so it's compressed by a distance of 0.121 meters. And then you can solve this for an answer. I'm going to put this into Wolfram. So we have 4.8 times 9.8 times 0.52 minus 0.5 times 1 times 0.121 quantity squared. And this gives us an answer of about 24.45 joules. So this is 24.45 joules. And that means that so the difference between our initial energy, how much we started with, and how much we ended is 24.45, because we assume that the energy due to friction was lost. That friction, that heat, that sound, whatever, those vibrations, those were lost to the rest of the world, no longer in our system. That was due to friction. And we want to find the work done by friction. Work is defined as integral F dot dr, which if you have a constant force, it will be force times distance. So I'm going to say that this might be kind of funny. It's difficult here to know what the sign is supposed to be. I'm going to say that the energy lost, the work from friction is negative 24.45, because the motion of the block is this direction. The force of friction is going to oppose motion. Friction always opposes motion. And so I'm going to say that, so this dot product here, since they're out of the angle between the force vector and the displacement vector is pi, or 180 degrees. Dot product is basically the cosine of the angle between, so basically -1. I'm going to say it's negative. That might be the answer they're looking for, might not be. It's kind of hard to tell with these. Hopefully you have multiple guesses. All right, and then asks, will the block be able to go back to its original position? So in this case, friction is not considered a conservative force. We're not getting that energy back. So the potential energy here is converted to kinetic energy as it goes down the ramp. Then it converts that kinetic energy into potential energy again in the spring, and the spring kicks it back up, converting back to kinetic, and then back up to potential due to gravity. Well, since we lost some energy to friction, we're not going to be able to get the same height as before, because some of the energy that we converted over to the spring is not going to all be converted back into gravitational potential energy. So it's not going to reach the same height. So will the block be able to make it back to its original position? No. No, it will not. So hope that helped. See you next time.